Because at that time, I had just been. I mean, who knows?
It's already blown out. It's already blown out.
That was also just about me. I realized this semester I felt like compared. I didn't know that at the time.
No, so I'll tell you what.
That's like
How I felt about you.
giving you
You were going in the hall.
It's unfortunate. I don't think I have way back.
Culture.
Oh, I know.
就一个另外几个我当时学到知道我怎么办。
It's more like the understanding is that I am a figurehead. It's okay.
我要酱牛奶。
As long as that's the understanding.
Test 1, 2, 3. Sorry, I'm a little late because of traffic. There was some accident. But are you guys? Well, what a drama for last lecture for me in this class. Are you ready for the midterm?
Not today.
Okay. So we have CCA to cover today. And while I'm setting things up, I want to just go over the bulk of the material, what you need to understand. First of all, from probabilistic point of view, we have two camps. What are they? Probabilistic view of regression. What do we? Maximum likelihood estimation. What's the other one? MAP, right? So there are two camps. So what approaches fall into MLE camp? We have, what are the candidates? Least square, OLS, say polynomial regression, say ridge regression, say generalized least square, say Tikhonov regularization. How do you put them in the camps? Which belong to MLE? OLS? GLS? Yes or no, already forgot. So what is so generalized about GLS compared to OLS? What is GLS trying to do that OLS cannot? Yes. What does that mean? What is correlation in the data? What's the intuition? Is this some correlation? If I have X, is correlation on rows or columns of X?
Columns of X, so you want to see if your data, the data that you're gathering are dependent on
Certain noise or correlation.
Who agrees with the answer? Correlation among columns.
Just a noise, right?
Who goes for the other answer? Correlation among rows. Who thinks neither rows nor columns? What else is there? Color noise, meaning, if it's independent noise, the noise in Y1 has nothing to do with the noise in Y2. right? Color noise mean if the noise in Y1, I know that there's more noise in Y1, I'm probably, if it's positive correlation, there'll be more noise in Y2 as well. So it's between instances, right? So what about Tikhonov regularization? What does it try to address? Gaussian distribution in what?
The weight.
The observation noise?
You want to change it to your data to noises. Like why told that someone could see which sees like random movement that is depending on each other. You take that out and you make it another multiply that out.
Okay.
Signal that makes one half.
Tikhonov handles dependent weights. It belongs to the map camp. It deals with generic Gaussian models for the weights. Yeah? It's not observation noise. Color noise handles that. Okay? So I just give you some idea. You should have grasp of the big picture. Two camps, which belongs to which, what's the meaning of that? Okay? And then the basics. Kernel being PSD, what does that mean? Positive semi-definite. What does that mean? That's something to do with linear algebra. Okay? So if I give you a matrix, can you tell it's a PSD or not? Okay? Okay, today, we have something exciting to talk about, as with every lecture. Last time we started with the caveats of PCA. PCA is very sensitive to scaling. And in reality, the scale is something that, you know, the scale issue arises in many different guises. In practice, they are very important. We are going to talk about CCA today, which addresses that caveat. The criteria is try to maximize so-called Pearson correlation coefficient. Once we understand the objective, it's a scalar function. And then we can talk about how to find the vector directions in the data that has maximum correlation. Then we're going to talk about, just like we have eigenface, we also have an example of application of CCA in the image denoising domain. The scale issue in linear regression is that you might have different sets of measurements. Oh. Why is it not getting it? It was fine earlier, right? Sure, whatever works. Let's do that. Okay, you have height, you have weight, you have different units. Each could take, different units, and how are you going to do? What are you going to do about it? And then you have this feature engineering. You want to augment polynomial features. So if x is height, if you do x to the cube, that's a height. The units are different now, and they're not comparable. I mean, to the system, it's just a bunch of numbers, but the units are drastically different. Some come with the data, some is what you engineered in order to have better regression algorithm or results. And then for each, you could have a choice of meter or inch, all these make a difference. Not practically, but in terms of the algorithm, they make a difference. So how do you deal with different types of measurements, height and weights? One thing people do is so-called feature standardization. If I know that they're just different measurements, what they do is they subtract the mean of each column-wise, and then they figure out the standard deviation, and then they do x minus mu divided by sigma. So after this transformation, this is per column. Each column, each feature will have this 0, 1, 0 mean and the standard deviation 1. So this is called standardization. What's the problem with that? The problem with that is sometimes the different measurements may have different significance, and that information is gone. If they are really on par with each other, but just because the range may be different by such a standardization, that information is lost. Some signal may be just random signal. After you standardize, initially very small magnitude. After you standardize, it becomes huge compared to before. Okay. The second problem, you have feature engineering. So this, again, using the same trick. So data matrix conditioning. If the x is between -1 and 1, you do x raised to the power of 10. It's going to be fractionally small. And what you want to do is you want to use this trick, standardization. It helps conditioning. But is that what you want? You have the same problem as the first one. And then, how do you do the different weights, different units, and all that? Here's an example. I have x and y, okay? And I can see the major axis indicated in the green line, right? It's elongated in a particular direction. And the blue curve is my Rayleigh quotient, the function value of Rayleigh quotient, capturing the PCA criterion value. Now, on the right, I decide to change the units of these measurements. X is scaled by 2.5, and Y is scaled by 0.25. Nothing fundamentally has changed. I'm just changing the units. Now, instead of almost a vertical ellipse, it becomes horizontal ellipse. So if I do the PCA, the axis will be the green horizontal line. If I have to do feature dimensionality reduction, I will choose x1 instead of x2. So the conclusion completely flipped. Okay? So CCA, remarkable property of CCA is it's scale invariant. You don't need to worry about scale among different measurements. given two sets of random variables, there are correlations among the variables. CCA finds a linear combination of each set. You have two sets, okay, which have maximum linear correlation with each other. And it's invariant to scaling. CCA deals with two data sets. PCA only deals with single data set, X. CCA, you always need two data sets, X and Y. X, Y have to come in pairs, meaning you have, for example, in video, you have images in one domain, you have audio in the other domain, but they always come together. Every time instance you have an image, you also have an audio signal. It has to be paired. It cannot be just random collection of data. It's paired, but the features in X, you don't have to have same number of features in X and Y. They can be totally different. For example, images and audio signals. Images you have, say, 500,000 pixels. Audio just 1D signal. That's okay. So let's consider a case where X and Y are perfectly correlated. So I have something, the common thing is Z, okay? But this extra for X, it contains extra measurements which are just purely noise. But the noise is so significant, the variance of noise is way greater than the signal, Z, okay? And Y is just Z. So in this case, if I could locate a subset of Z, a subset in X that correspond to the first part, which is Z, I would declare X and Y perfectly correlated, right? If there's an approach for me to accomplish that. But if I want to, do denoising with the PCA on X alone, then the PCA would pick the noise over Z, because noise has much more variation than the signal Z. And then if I do regression over the PCA of X against the Y, then it will result in very poor correlation. That's not intended, okay? As with the Bayesian view, the probabilistic view of all these regression methods, a generative model helps us understand the concept of CCA. CCA assumes there's a common latent space H. We use H. It indicates something hidden, okay? There's a meaning to it. I don't just randomly pick a letter. And then there's a separate latent space for X and Y, ZX and ZY. H, ZX, ZY are independent of each other. And the X and Y are observations. Each is a linear mixing from the common latent space. For H, it's mixing through some U, some linear transformation. For Z, is you can think of IDY noise with some linear transformation, okay? The thing is they are independent of each other. Likewise, for Y, it's a different kind of linear transformation over the common latent space H. And then this is something else, which is independent of H. So if I write it out as matrix form, is of the following. Because here P and Q, the features, may not be, it does not require P equals Q. In the case of video and audio, the visual frames and audio in the same video, you can think most likely the P and Q are not the same. X and Y may not even live in the same feature space, okay? What's important is always assume paired data. If you have n instances, I also have n instances. And it's 1 for 1. You know the counterpart. That correspondence has to be there. So let's see an example. My hidden space is just a scalar. H is just a scalar. It's a Gaussian distribution in the scalar, okay? And xc and yc is this common component for x and y. And in this case, there's a linear correlation. Remember, we have x equals h times u, is it u? Yeah, h times u, y equals h times v plus something with some noise, okay? H in this case is just some scalar, okay? Some a or something. U and v in this case, you know, it becomes just a scalar. It's a slope. Okay. In this case, this line is actually perfect. Just k equals 1 in this case. So in a way, it's just this plus some noise. Okay. Now I have used color coding to indicate the perfect correlation. The cool color is when the scalar is a small value, and the hotter and warmer color goes to a larger value. Okay? So if I observe that component in X, if I know that it's colored blue, I know the counterpart in Y space is also blue. Or if it's blue, I know both of them are small value. If they are warmer color, I know the values are large. Okay, so this is the signal in my X and Y. Okay, CC is trying to discover this correlation between X, Y, even though we add a noise to each X space and Y space separately and independently. So this is when we add noise, things become tricky. Remember, so this is X space. I have two measurements for X. Initially, my common space is just a scalar. So I color coded them, okay? You can think of it's this. Initially, all these points live on this line. If I project them, this is the value, okay? I color coded them, yeah? If noise is 0, it's just like this, it just lie on this. And because the perfect correlation, you can think of initially the data. So if this is actually my XC, here this is XC and YC, okay? I'm studying between the two spaces. Here, what I observed is something separate, X and Y, okay? But X, the observed, I have two measurements out of XC, which is common. I add some random noise to it. So you can think of this is my XN dimension. This is my XN. Initially, it's this. Initially, they all live along the XC line. But because I add some noise to it, I introduce second dimension, which is irrelevant to XC. These points start to, some points jump up like this, some jump this much. This is just noise. And this is just to make look appear to be complicated. I added rotation. So this oblique coordinate system, I have a change. Initially, you can think it's upright. I turn by alpha degrees. Okay? So what I get in the end, x1 and x2, each is a mixing of xc and ym. x1 is cosine alpha times xc plus sine alpha times xn. Okay? I do the same thing for yc and yn. Initially, it really just is yc, then I add some noise to it, yn, okay? Initially, just some data, Gaussian distributed. I add some yn to it, so it starts to jump up and down based on Gaussian distribution. And then I just rotate like this by angle beta, okay? So how do I identify, how do I know that these data are correlated when I examine them side by side? It's the color coding that gives away, right? I color these points according to the latent space, which is common, the correlated part. And this is in fact indicated by the size of the value. So for example, I know this point. If I can find that, maybe it probably corresponds to this guy, right? They have the same color map. They come in pairs. That's why it's very important. Okay? But in reality, you only know they come in pair, but you don't know the correlation. Okay? Any questions at this point? You need to understand how the data is generated. If I'm able to squash all the noise in the xn and yn respectively, if I just kill all the noise, project onto this xc axis, and all the points project to yc axis, I will be able to discover perfect correlation, because if I plot xc and yc together, I will just get a line like this. Right? Okay. Okay. So covariance and Pearson's correlation coefficient. Covariance is this definition we know already familiar with. And we know that if x and y are independent, the covariance is 0. Okay? But if covariance is 0, does that mean x and y are independent? No, that's good, very good. So the Pearson's correlation coefficient is defined by the covariance of x and y divided by the square root of x covariance and y's covariance. Essentially, it's the variance of each. So in a way, it's a covariance calibrated by the amount of variation within each set. Okay? And because of this x and y completely symmetrical in this definition, the correlation coefficient itself is symmetrical. And with the Cauchy-Schwarz inequality, you can prove the range of rho is between -1 and 1. What's important is whenever this comes to math, this comes to your coding. When you divide this by something, or when you need to solve the inverse of matrix, you have to check, can you actually do that? Rho, it will not be defined if any of this denominator is 0. It's just not undefined. You can't say that, oh, maybe this is 0, this is 0 and a 0, maybe it's 0. No, it's just undefined. Because it's just, there's no variation. You can't say anything about it. Okay, undefined, not available. It's not the same as 0. Okay? So Pearson's correlation detects only linear dependencies. So what does that mean? Let's take x and y. Covariance always do first need to center the data. Let's subtract the mean of each. If they are perfectly linearly correlated, y is a centered version, y is a k, slope k over x. Then if I plug that into the correlation coefficient definition, this ksy, and that will become, this is just k, x times ex, right? Kx. And you can show that this is just k, variance of x, because this is constant, right? When you take the expectation, doesn't matter. So it's just a variance of k. And likewise, this, you can plug that in, the co-yy can be expressed using x covariance as well. So that cancels out. The only thing is that because this k, if k is positive, this will be +1. If k is negative, when you do square root, this comes out to the absolute value of k. So it will become -1. What does that mean? If x and y are perfectly correlated, like the k there, what the actual slope value doesn't matter. If it's 0 degree, 45 degree, 30 degree, it doesn't really matter. Correlation coefficient is 1. Perfect correlation meaning, given x, you can perfectly predict y based on a linear relationship. That's what it's about. If it's less than perfect, it means that if I use a linear prediction based on x value, I can say something about y, but it's not perfect. So no linear relationship can predict that correlation. but it has nothing to do with slope value, okay? If x and y are independent, so we know cov x and y will be 0, right? We know that, so rho has to be 0. Independent meaning you can't predict y based on x, or the other way around. If it's rho is 0, if you conversely, you can only say, if the rho is 0, you can only say x, y are linearly or uncorrelated. That's the best you can say. But they can be non-linearly correlated and perfectly dependent. One example is y equals x squared, okay? And ex is 0. So a 1D case will be some, this is, everything's 1D. It's just like that, okay? Why is that? Because when you calculate, it's 0 mean. When you calculate the cove x and y, essentially you are taking the expectation over x, because it's 0 mean, I'm not gonna worry about the mean, so it's this, expectation x and y. So for every x that's a positive, so here you have x, you have y, and you have a counterpart, which is minus x and y, right? You always have another part. So this will be something of x and y. If I split them by that, it will be x and y. There's another part of this x greater than 0, you have x less than 0, there's x and y. So you have one term in the other side to cancel you out, because y is the same positive value, but x, one is positive, the other is negative. When they add up together, it's 0. Questions? Do you understand why? In this case, if I give you a curve like this, it's the correlation is 0. Yeah? It's symmetrical with respect to this axis. Because every term here, you have this term to cancel out in the numerator. So if rho is 0, when x and y jointly normal, uncorrelatedness is equivalent to independence, because Gaussians only determined by the first two order moments, expectation and the covariance. Okay? So here's some example. So all of these at the bottom row, you can see they have a symmetry in it, right? So this is a case, they are 0 correlation, just means they are not linearly correlated. What is linear correlation? It just means if x increases, y has a tendency to increase, or has tendency to go down, to decrease. 0 means you can't say it could go up, could go down, most, it evens out. There's no trend, particular trend. And this is exactly that, you can understand from math, you can understand really from the intuition what it means to be linearly correlated. It's either this or that. Anything that's flat, 0 correlation. Okay? And see this? Missing a number. Why is that? Vy is 0, right? Variance of y is 0. It's undefined. Rho is undefined. That's why there's no number. Okay? And this is to show that it doesn't matter, the size or the slope of the line. They are perfectly correlated. And this is, as x increases, y goes down, -1. And this is a positive slope, is +1 correlation. Here shows example where the rho is between -1 and 1. You have some noise. There's no way you can predict. If I give you x, you can only predict maybe the best is this value, the mean value. But there's always something you cannot predict perfectly. The factor, the more spread along the y, along this direction, this is much smaller, this spread much bigger, the correlation is becoming weaker. Given a data set like this, this is just a sample, empirical estimation of this cove xy divided by the vx vy, okay? This is just expectation, this is just a sample estimation of this. We call it the sample correlation coefficient. in the fifth homework that will be released, which will be due in 1 week, we have 3 problems, Rayleigh quotients, correlation coefficients, and CCA. The derivation is simple, and everything related to correlation coefficient and the CCA, the answer is right there in the slides. I want you to even to copy, you understand the steps in this reasoning. And then I just ask you to code up this correlation coefficient. We will give you some data sets so you can run this and figure out the value, establish your intuition, the grasp of the concept. And you can play with the numbers, how the data is. We give you the code for generating synthetic data. You can play with the numbers there, and you can see how the correlation will change. So this key concept of correlation coefficient is that it's alpha invariant in the following sense. If I stretch x and y, scale it, and add some offset to it, okay? The magnitude of that won't change, okay? In detail, if I can show, based on this definition, A and B are just, C and D, because cove and variance, they all do the centering, so this constant not gonna matter. So it becomes this. And A and B are just constant, you can take them out. And for the variance, you will have A square and B square. When you take them out, because it's always positive, you have the absolute value of the product AB. So then, if AB is greater than 0, it's just roll AX BY. If it's less than 0, this will be minus the original value. And if AB is 0, then it's not defined. Okay? Okay. So for Gaussian distribution, we have introduced this notation when we study multivariate Gaussian. In general, you have this, covariance matrix, but we can, for these off-diagonal terms, I'm going to use this role, use sigma x and sigma y to factorize this term. So then it becomes, this is exactly sigma xy divided by sigma x and sigma y. It conforms to our correlation coefficient definition. So for Gaussian distribution, it has very nice interpretation. That is because, Gaussian is just determined by the first 2 order moments, and the covariance, that's the only thing it has. And the rho is defined by the cross, the covariance and the covariance within each set. Okay. So if I do this, this is essentially sort of like this, but only taking the diagonal. If you can think of sigma x, sigma y is the amount of variation within x measurements and y, or heights and weights, how much variation you have within each. This is like intrinsic variation within each feature. If I use this this is like the feature standardization, use this to normalize the measurements, all I have is, remember, if it's this, if it's this is Gaussian, if I apply a linear transformation, the variance will be AXA transpose, right? This is some basic thing you need to remember. And then we can just multiply this A transpose here. In the end, you will get to this, much simplified. So you can think of this rho is fundamental to the shape of Gaussian. It's the relative proportion. If rho is 0, uncorrelated, right? So this is example here. If rho is 0, so this is the standardized version. In the sample version becomes R. So it's this, sorry. So R determines everything. If R is 0, just a perfect disk. If it's 3D, it's just perfect ball. If it's 0.5, you can see that there's correlation along x equals y direction. Okay? Sorry, this is the spread what we are talking about, has nothing to do with the slopes. If it's 1, it's perfect correlation. You can, given height, you can predict weight, for example, perfectly. So on that note, I want to re-mention the PCA, right? If you are given height and weight, you have, if let's say this is your data, and you find your PCA. So what does PCA really mean? If this is height, this is weight. This says, what is this pattern? This is my first PCA. This pattern says, you know, if my height is certain value, I can predict weight as k times height. So if you come to this dire situation, you can only keep one measurement. You can simply just, you know, take height, for example, or take this dimension, right? There's a pattern. You know, this line is height, you know, k times height plus some offset, right? Or if it's 0 mean, you know, it's just k times height. This is a particular pattern, right? So if I take this as my measurements, as my direction, even if I just take the value here, you know, I just need this one measurement. Yes, I throw away, you know, if I predict, given height, I can predict this, but this is not perfect because the points, they may be somewhere here. I'm losing this much variation. But this is this, you know, I capture the major variation. The major XY correlation is captured in the first PCA, right? I'm throwing away the slight, you know, perturbation along this axis, right? So it's, PCA is capturing this covariant patterns between the dimensions. Because if I have 100 dimensions, if I capture the 100 such correlations, I just need to know the size of this pattern. I don't need this 100 numbers. I just need one number on that. I lose something, but it's not a lot. Okay, so this is my, you know, perfect correlation 1, -1 going the other way. And this has some spread. Now I can't perfectly predict, there's always some noise. And this is, I can't predict at all, uncorrelated. Same Gaussian points, okay? I have my, I generated X and Y. And this is to do the AX BY thing, okay? I'm stretching each dimension. And now this looks like that. You know, if it's 1 and a 3. If it's a 3 and a 1, it becomes horizontal, okay? So if you look at this pattern, all these has the same correlation, 0. This has the same correlation, which is -0.5, okay? This is a little bit, you know, not as intuitive. Sometimes we look at this, you know, we tend to mistaken the correlation to the slope of correlation, right? So the correlation coefficient really normalizes this covariance by this intrinsic variation within each dimension. This looks like a ball. We can perfectly say this is uncorrelated, XY uncorrelated. But when we look at this, it seems like there's a pattern, right? Or even this. This, in a way, this is upright cloud. We know the correlation is 0, linear correlation. But when we look at this, somehow we feel the slope has something to say with the size of correlation coefficient. No, there's nothing to do with it. So sometimes it's good to visualize, but you have to understand what are you visualizing. Sometimes don't let this misguide you. Okay, CCA. So we have covered correlation coefficient. That is a scalar. We are dealing with X and Y. It's just a random variable, 1D vector, 1D scalar. Now we are talking about the data matrix n times P and n times Q. And 0 mean m paired points in P and Q dimensions, respectively. CCA is to try to simultaneously find a projection direction U for X and V for Y, such that when the data x projected according to u, v projected onto v, y projected to v, you calculate, now becomes, when you have one axis, when you project, doesn't matter how high dimension that is, it just becomes a scalar, set of points, 1D points. Now this is what we have learned, right? Given random variables, scalar variables, we calculate the correlation coefficient. And we want to maximize this value. So we plug that in, it becomes this, okay? If it's a zero mean, all this expectation is gone, so it's very much simplified. So this is just looking for, just like PCA, we first introduced the concept of one PCA, and then extend it to KPCA. Likewise for CCA, we can also seek the first KP CCAs, so you can seek a Lacan subspace K dimension. K though has to be less than the P and Q dimensions, okay? So where total projective correlation is maximized, okay? CCA is invariant to scaling or affine transformation. So that actually is of a different reason. If U star, V star are the optimal projections for X and Y, okay? So it maximizes this score. It means this, and then it maximizes this thing. If X and Y are linearly transformed, I'm stretching X any way I want, linear transformation, sharing, all this is captured by linear transformation, they're independent of each other. The optimal correlation value will not change. The reason is that, if it's transformed, for the X star, X tilde and Y tilde, the CC of that, we are trying to maximize this value, right? We're trying to find U and V. After you project to this, is maximum. But X tilde is XA, okay? And if I reparameterize U, assume A and B are full rank, the inverse exists. If I just use the optimal values, A inverse, okay? And this use the B inverse of that. These two will cancel out. And this is just this. And we know this value. So basically, when X tilde and Y tilde projected onto A inverse U star and B inverse V star, this will achieve the maximum correlation, just as U and V can achieve the maximum CCA correlation for X and Y. You can warp X and Y any way you want. There's a counterpart change in the optical axis. They will cancel each other out, and the resulting correlation, the maximum value, remains the same. The reason for affine invariance of CCA is not, not the same as the previous affine invariance of the correlation coefficient, but this has something to do with the linear transformation. There's always a counterpart. You can always find the counterpart of the axis, so they cancel each other out. Okay. So the optimal projection are transformed accordingly. So this is the maximum of that. So how do we solve this? We have a criteria. It's we formulate into a constrained optimization problem because quotient is very difficult to study. So we want to, same thing with the PCA. We want to maximize this, but we can choose that, each of this, because X, Y independent of each other. U is for X, V is for Y. We can apply the same trick. We assume it's 1, okay? Just like in the Rayleigh quotient case. Because if it's not 1, I do any scaling, K times ku, it will be canceled out from the numerator. So this will also become ku. So the size of that is inconsequential. And Cx, Cy is just the sample estimate of the covariance of these matrices. Now we have the Lagrangian objective minus the first constraint with the dual A over that, and then B over the second constraint, okay? And then we do a partial derivative with respect to all these variables, and you can check this. It's very simple. It's just quadratic form. At the most, you have this linear terms. In the end, you have, you tidy up the math. It becomes this, and if you do the partial L, partial A, it just gives you the constraints itself. Now, I have this equation. If I do this U transpose on both sides, I will have U transpose CXXU, and we know from the constraints it's 1, so it becomes A. Likewise, if we multiply this by V transpose on both sides, we will have this equals B times this, and this is 1 equals B. Now, these two are just, this is a quadratic form, it's a scalar. So this value is just, this value is a transpose, it's a scalar, so they are identical. So then we show that A and B A has to equal to B, and now we just call it lambda. So now, if this is lambda, what do we have? According to this equation, Cxs V equals lambda Cxsu. Likewise, for the next equation, Cyxu equals lambda Cyyv. And we know by the definition, the cross correlation is transpose of each other. So we have very simple, we just write this into matrix form. It becomes like this. That means the optimal solution has to satisfy this, okay? And this is so-called, we've learned Rayleigh quotient, generalized Rayleigh quotient. If this is M, this is D, M, V equals lambda D times V. This is generalized eigenvalue problem. Most time we deal with D equals I, but in this case, it's the variance on the diagonal. And we know the solution for that when we learn the Rayleigh quotient. The solution is a generalized eigenvalue, the pair of matrix, okay? Defined as such. It's maximized when the U and V takes the generalized eigenvector of this matrix pair, and the corresponding eigenvalue is a criterion value. So we can look at this, and it gives unifying view to a bunch of eigen approaches. PCA, and there's other things I grayed out. We are not going to talk about them. You just need to know that it's not more than just PCA and CCA. They're a bunch of approach. They all share the same generalized eigen solution for the Rayleigh quotient optimization. The only difference is what is their M, what is their D. For PCA and TLS, it's using CXS and essentially CXS W times V times a lambda V, right? It's finding the eigenvector of the covariance matrix. For CCA, it always involves data sets X and Y. It's the cross correlation with D is the covariance matrix. So now, let's try to understand the structure of the eigenvector solution. I want to give two preps to that to interpretation. One is that if X, the SVD of X is UI, VI, SI, basically it's X equals U, SV transpose, okay? We have done this before. This means XVI equals SUI, right? You apply to the right singular value in a vector, it gives you the left singular vector. And if you multiply X transpose to the side, it will give you, it's completely dual to each other, it's symmetrical. Now, which means that, I can write out jointly, x, I just unify these into this matrix equation, it becomes this. X transpose in the off diagonal, Ui and Vi stack them together. Ui and Vi, they may have different dimensions, but they always have the same number, right? So if m times n, m times n times m is m times n, v is n times n. Sorry, I have to look at it, the paired vector. So this is just one vector. This may be a smallish, maybe different dimension. Okay, you can always write it as such. But this is just definition of eigenvector. So what this means is, you can think of this means that I can stack the left and the right singular vectors together. If I look at this instant space and the feature space together, this is and the singular value together, they are actually the eigenvector of this cross-diagonal matrix. This is a perfectly symmetrical matrix. Okay, that's a different view of, linking SVD with eigenvector, eigendecomposition in a expanded space. That's one, okay? The second prep is this. I have a matrix M. I want to find a U and a V that maximize this quadratic term. U and V are, you can think of projection, it's unit norm. Okay, I call this a line. I will tell you why. You will see when you follow through the derivation, it's just align the U and V according to the metric M. If M is I, when will U transpose V maximized? When will this be maximized? U and V are both unit vectors. When U equals V, right? Dot product, it has to be the same. Anything like that, perpendicular is 0, and this will be -1, right? They have to be the same. So that's, really most of the time, just like when we develop PCA, we always start with the most degenerate case. We make it more and more complicated, from uncorrelated to different size of variance, and then we have general correlation. Same thing like this. So from this, you can see why this is called a line. Because if it's just a degenerate case, it just means the U and the V has to be aligned. If M is a little bit skewed, this may not be the best solution, but whatever optimize this criteria, make sure that they are aligned in order to maximize this metric. So how do we go about this? If we go for SVD of M, you have this, and we are going to parameterize U and V, because U and V are on the left and right side of M, they have different dimension, right? But I'm going to parameterize according to M's intrinsic coordinate system, U and V. So U times alpha, V times beta. It's a proper coordinate system. U and V are orthonormal. Because U and V are unit length, we have these constraints, right? The orthonormal transformation doesn't change in length, so alpha beta has to equal 1. Now this becomes this, and we know this will be diagonalize M. So it becomes this as a diagonal matrix. So this, we are facing a situation, alpha is a vector, S beta is a vector of the same length, right? It's a dot product between S alpha and S beta, just like the case of U and V. When will be this maximized? When alpha equals S beta, right? Just like this case, when is this optimized? It's U equals V, right? Yes? Okay? Now what does that mean, S equals S beta? It means it can be written as S beta divided by the norm, because we know alpha is unit length, right? So it we must be able to write alpha in terms of S beta divided by S beta just to satisfy this unit length constraint. Now, S beta transpose together becomes, these two becomes S beta squared. So that divided by it leaves this S beta norm. And that becomes this. Now we have a situation, according to this, beta 1 square, all the way plus beta whatever n square equals 1. So now we have the same situation like the PCA. This is a weighted average of singular values, right? Betas each is a sum up to be 1 and non-negative. And this is just weighted average of this. So when will this be maximized? You put all the x in one basket, the one with the largest singular values, right? So this will, the weighted average is always then the maximum. In this case, S is ordered, so the maximum is S1, okay? So when will this happen? When beta has to be 1 and alpha has to be 1. And then we get U is U1 and V is V1, okay? So now let's understand the solution. We understand the solution for CCA is just solving the generalized eigenvector problem. But how can I understand the structure of the solution? You know, this generalized thing, we really have trouble understanding. We understand eigenvector better. So we break this. We break this into, you know, we normalize this. We break, if this is my C, I'm gonna do C half and half, right? So it's a lambda C half U and V. I'm gonna move this to this side. So this becomes this. And this I just copy over. And then just to make this symmetrical, I also do this half thing. But I don't have half here, so I need to compensate it with the other half, right? So this is completely identical to this. And this, I moved half over, so I am still left with a half, okay? Now you can see that this is identical. I might as well define my tilde U and V is the scaled version of the original U and V. So this becomes UV tilde, UV tilde. And this is just the matrix I have to deal with. And this is just diagonal. If you multiply matrix by a diagonal on the left, it just scale the rows by these values. You multiply by on the right, you just scale the columns by this. So in the end, it becomes just this, right? So this thing becomes this, and this is rewritten as U, and this is just this, simplified. Now, according to our first prep, you know, this thing, you can think of the eigenvector of this is simply SVD of this matrix. Remember the prep, the first one? So step 2 is just solve this U tilde and V tilde is simply SVD of this matrix. I go to the expanded space to seek a simpler solution. Because of the connection between SVD eigenvector, I come back to the space I'm more familiar with, the lowest dimensional space. And then once I have tilde U and tilde V, I just need to reverse the process. Inverse that, get the U and V in the original space. Okay? So let's understand these two steps are easy to understand. There's not much to do, right? You just, once you have that. But what does this step mean, okay? When I have U tilde V tilde, remember the scale invariance, the alpha invariance of CCA. It induces a counterpart change in XY. It corresponding to the XY will be scaled by this, the inverse of this. This is a half, this is a minus half. Change of coordinates of XY. What does that mean? I'm trying to optimize this objective. This is never going to change. When I introduce this essentially says U tilde is CXXU. I have a different representation for this, but I want to solve this. So in order to keep it constant, I need to do the equivalent change on this side so that this doesn't change. Likewise for y. So I might as well introduce this, this is my x tilde. So it becomes x tilde u tilde and y tilde u tilde, v tilde. And you can show that, you transform u and v, x and y accordingly. You plug in everything, the cross correlation takes this particular form. It's essentially this middle term becomes this term, which is exactly the Cx, Cx, the covariance between the transformed x and y, okay? And if you calculate the transformed x and calculate the covariance matrix, it becomes I. And the covariance of the transformed y, it becomes I. Okay? That is, x tilde and y tilde are whitened in their own spaces, decorrelated, isotropic along all the directions. Okay? So you can check, you can check out the math offline, and that's why we put it into the assignment. You just literally just copy this slide. It fulfills your, assignment. But I want you to understand the intuition. This is so remember, this is our original data, okay? X1, Y1, X1, X2, the measurements in X. Y1, Y2, that's the original data. What does the whitening do, right? The whitening gives me this. Back, forth, back, forth. Do you see the expansion? It might look better when you do it on your own screen. Initially, just focus on this side. This is elongated. After you whiten, it becomes a disk. You can see it literally only expands in this direction. This, it doesn't change, doesn't change much. It depends on actually it will change because it's scaled so that the covariance is 1. Okay? So now, in a way, initially, I have to deal with the correlation coefficient. I have a numerator, I have a denominator. Every time I change u and v, both will change. Now, because it's whitened, no matter which direction I project, the variance, it's always 1. I don't need to worry about the denominator anymore. I just need to worry about the numerator. They should be perfectly aligned and maximize the correlation. That's the intuition. So in this whitened space, I calculate the SVD of this whitened matrix, right? I just calculate SVD. So I have U and then V and then S, right? U goes to that and V goes to that. Each has 2 components. The thicker green line is U1. This is U2, and this is a V1. This is V2. And you can see that it's a good sanity check, because what does this align mean? Alignment means that U1 is pointing. Why do I color the dots in such a way? Because the coloring tells me how the latent space, the variable, is varying. I know the blue dots are small value, the red dots are large value, and U1 is pointing from large latent space variable to small latent variable. And this direction is exactly, there's no other components. All this direction is just noise. There's no correlation to it. It's not skewed like this, right? It's perfectly pointing in the direction. It's in the gradient direction of the color. Likewise, this is in the gradient direction of color, and it's not flipped. If it's flipped, it will have the minimum cross correlation, right? It's pointing from red color to blue color, like here, red color to blue color. It's trying to align the 2 space according to the latent space vector, the scalar, indicated by the coloring on these dots. Now the third step is to back project. In this case, my x, c, and y, the XM, the noise orthogonal. So, you know, here, because it's SVD, this is completely orthogonal. This, in this particular case, the back projection, this still remains perpendicular, okay? Just change your variable. So this is a pipeline for training, right? You have, you know, sorry, I probably staple. Yeah, if I have training, zero mean training data, I compute CCA, okay? Through these 3 steps, whitening, align, back projection, I solve the thing. It's the way of understanding this. In a way, it's CCA just to solve this, you know, the generalized eigenvector of CXX, CYY, CXY, CYX, just this, right? By math, it's just that, easy. Once I solve that, I can compute their projection. X project onto U, Y project onto V. This is also zero mean. If I want to do regression, given XC and YC, I can fit K by K linear aggressor on the coefficients because I know now XC and YC supposedly lie in this perfectly correlated, maximum correlated space. So I can relate them with the linear transformation. And this I can use the OLS, and that's my solution. And you can plug back with how you get your XC and YC, it's this equation. This is training. Find the CCA, project into each space, and plot them together. You can find the correlation, linear transformation linking them. At the test time, test points project onto XC. And with the linear prediction, you can predict what the counterpart in the Y space should be, the coefficient should be. And then you can predict Y test from projection. You can do something like that. You know the projection, and you can, it's onto this space. You can get it back. You know, this just gives you this coefficient, but you have to get it back. This is just one number. You need to get back the vector, so you need to multiply. In the K space, you know, V, in the original space, it may not be orthogonal. So this is a math. If you have non-orthogonal V, and you want to find the so-called bio-orthogonal basis, so that as if they don't exist, this V can be solved as this. This is how we get this equation, okay? So how do we use CCA to make a prediction? It's great to find the latent space, but the purpose of this is to make the regression more effectively. If you are given the data, most of the times, the naive approach is just to go for OLS, right? You are given X and Y, it's a regression problem. You can just do the regression solution. This is training data, you can figure out the OLS solution with this, and then when test data come in, you predict with that. That's our baseline. CCA coefficient regression, use XC, you try to predict YC. With YC, you can reconstruct the value in Y. So we can basically take this previous slide, collect them all together, expand them. Essentially, you have this. This is test data, project to CCA in X. This is a coefficient regression, XC to YC. This is, once you have YC, it's just a coefficient on the Y space, but you need to use V to come back to recover the vector form of it, okay? But there's a third way. I'm gonna start with the coefficient. I need to go to projection in X space because I want to find the latent space. If I use X, it's not just the noise thing we have talked about. In the TLS, we have noisy X, right? This is, you have a whole lot of measurements. You have another irrelevant dimensions, which may be structured, that are linearly mixed with your X. So with CCA, I find the projection. I'm going to go for regression to Y, use OLC directly. Why don't I work with YC? Because at test time, I only have XC, X, I don't have Y. Okay? So then, it's just project to CCA in X, using U. And this is just really the instead of, regression to YC, I'm just regressing to Y directly. It's just OL solution, okay? Now, continue that example. We find our U1 and V1. We have X and Y projected to this line, okay? Now I have squashed all the noise. I discover this latent space automatically. And so this is just, each is just a number on this axis, right? This is my projection, XC, YC. It's just a scalar on this axis, right? I don't need to know how this line lies within X and Y space. I just need to take these values. And then I just plot them in the joint space, XC and YC. And this is my generator, remember? I showed you at the very beginning. That's how I generate the data. This is what I recovered. They line up perfectly. And they may have a scaling problem, but we know in correlation, the slope doesn't matter. Okay? Now, this is just discover CCA. If you want to use this for regression, remember the first option, X to Y regression, okay? This is my X, this is my Y, each is two-dimensional, okay? What I plotted here, for each point here, I learned that X times A goes to Y, that's my Y hat. For this point, I goes to something of the same color, maybe this point, with the same color, but it's a red circle, okay? So I overlay on Y. Y are the solid dots. The circles are my prediction, Y hat, predicted from X space, okay? You can see that it lines up nicely in this latent space. It has nothing along this noise dimension I added artificially. Yes? Okay. If I do CCA regression, this is OLS, which is okay, but pretty good results, in fact. If I do XC, YC to Y, okay? See, again, the same thing, my prediction lines up very neatly. But somehow it is not as stretched out like OLS. If I use XC to predict the training data Y directly, this is a much nicer solution. This is the pipeline of my regression thing. I'm going to show you some variation. Earlier, I have this cosine R as a rotation matrix. Now I'm going to add some off diagonal, so you can see this is a little bit initially, all the blue and the red, it's perpendicular mixing, but now I shared a little because of off diagonal. You can see the color is going like this. Likewise for this, okay? Now, again, we do the same thing. Given this data, we whiten each. Now each space, the data becomes a disk. In 3D, it will be a ball. And in the whitened space, I solve the SVD. Okay, I can find, again, you can see it's pointing out in the color gradient direction. This is U1, this is V1. And when I do the back projection, now, so here it's orthogonal because it's the SVD, U1 and U2 they have to be orthogonal. But once I do this, back projection, they may no longer be orthogonal. Okay, this is, U and V. Okay, PCA are always orthogonal. CCAs are not in the original data space. And in a way, you can think of it. It's interesting how the way it's trying to. If you project onto this, you can see that the color. There's no mixing in color. Yeah, this takes some time to sink in. I'd rather my slides to like a wine. The more you look at it, the more you learn from it. It takes time. I think the first time you need familiarity to understand it. But I hope that the slides will be helpful to you to understand the concepts. Okay, so that's the projection. What am I doing with time? What time? 32. Oh. That's fine. So there'll be some more, sorry. So there will be some more examples. I just want to show, so if you make it more complete, there's more examples. But I want to show you one image example. We can apply the same thing. Noisy image is my X, slightly cleaning version is my Y. The mean, the standard deviation, the CCA for this, nothing like what you have seen in PCA. CCA for Y, nothing like that. And the eigenvalues falls off like this. And my question for you is why it will always, it will go to this 0. And we don't need to understand the details of this, but you're welcome to. I will just want to show you one thing. This is my training samples of X, okay? Training samples of Y, okay? You can see it's, it's very small, 20 by 20, okay? This, you can't really see faces, can you? Very noisy version. And this is my Y. I trained from such data. And this is a test. So these data have never been seen during training, okay? So this is prediction, X to Y, the prediction. This is test. They don't look as good, okay? This is X to Y. This is the OLS solution. It looks okay on training, but not so well on the test. This is using coefficient regression. I can choose K. Test and training, you can't really tell, more or less the same. And if you use more K, training is better, test degrades. If you project to XC, from XC to predict Y, when this is this, you see the faces are much cleaner, even cleaner than your Y, right? Yes? And when you go for too much, you are not denoising it because S has a lot of noise. And so this is just to show testing samples X. From this, I'm able to predict this OLS solution. This is coefficient solution, and this is the CCA regression directed towards Y. Okay? I'll end with this. Thank you. Good luck with the meeting.